Thank you. Today I'm going to talk to you about, wrong keyboard. I'm going to talk to you about atmospheric emissions and regional air quality impacts from early stage Marcellus Shale development. This is a collaborative effort between the Darrell Group at Drexel University, Aerodyne Research, and the Electric Power Research Institute. So to start off, the Marcellus Shale is the largest shale play in the United States. It underlies a large part of the Appalachian region, as you can see in this map here. And it's estimated to contain about 84 trillion cubic feet of recoverable natural gas. Now, given its large size, it has the potential for up to 4 times more wells than any other shale play in the U.S. And as we know and why we're here, there's air quality and greenhouse gas concerns associated with shale gas development. So with all that in mind, in 2002, our team looked at or did mobile measurements in northeastern and southwestern Pennsylvania, both of which are regions that have high shale gas activity. And we went there with the objectives to quantify emissions from upstream activity, to understand the regional differences in the Marcellus, and then finally to characterize background concentrations during early development. So in the summer of 2012, the Aerodyne Mobile Laboratory was deployed with a suite of 1 Hertz instrumentation. We had gas phase measurements, including methane and ethane. I will note we only had ethane in the southwest portion of the state because it was being developed at the time. We had CO2, or CO, CO2, NOx, VOCs. VOCs were measured using a PTRMS. N2O and acetylene were used as tracer gases in this study, which I'll talk about in the next slide. We had particle phase measurements, including number concentration, mass concentration, composition, black carbon, and these 3 were measured using SPAMS. So using the mobile laboratory, we made measurements at specific sites, and then we also made measurements while driving throughout the region. Here's a table of the sites that we investigated. We looked at a number of compressor stations, production well pads, a gas processing facility, a drill rig, and also a completion. So tracer ratio methods were used to estimate emission rates at these sites we investigated. Scott Herndon just gave a really good description of this in the earlier session. So I'll go into a little bit of detail about it for the people that were not here for that session. Essentially what we did is we released tracers at the fence line of these sites. I'll just note we did not have site access. These tracers were released at a fixed rate. The mobile lab then would circle around the site and then would do multiple transects through this mixed plume area. Now these plume intercepts, which look something like this, where we would have co-located tracer species with our site emission species, could then be isolated. We would subtract the background, and then we would find the emission ratio of those species compared to our tracer species, either using linear regression or by using integration. So then the emission rates at these sites, they were estimated by taking the mean slope from those transects and simply multiplying it by the known tracer emission rate. I will say that there were likely some errors due to the fact that we were releasing the tracer offset from the site. So to correct for this, a first order correction factor was developed for this study, and it accounts for differences in plume dispersion due to the fact we're releasing from the fence line. It uses Gaussian dispersion theory, and it accounts for meteorology at each site. And I won't go into a lot of detail about this. In fact, I gave a fairly long description of it last year. But what I can talk to you about is the performance of our correction factor. And so if you look at this figure here of our correction factor versus the downwind distance, or where we were intercepting plumes, you can see that the correction factor stabilizes as the distance downwind increases, and the range of downwind distances for this study was somewhere in here. So we have a lot of confidence in our correction factor. And additionally, 94% of these corrections were within factor of 2. So then we can get to some results. Here is a figure on the right here that has the emission rates in metric tons per day for some select species. And this is for all of the sites we investigated: compressor stations, production well pads, and then the transient sites. Very important result from this study is we did not see enhancements of PTRMS VOCs downwind of any of these sites. That includes BTEX compounds and other non-alkane compounds that have been seen in other shale gas studies. And this is with the exception of methanol, as you can see here at this CF compressor station, and that was assumed to be used as a pipeline antifreeze at the site. Another important result is we did not see enhancements of submicron particle mass concentrations downwind of these sites. We did, however, see enhancements of particle number concentration at a lot of the non-production sites, and so this indicates that we are seeing fresh natural gas combustion. So going a little bit further, looking at the well pad emissions, the in-production well pads that we looked at had little or no emissions of CO or NOx. One site did, however. These sites had the lowest methane emissions of any of the sites we investigated, which was to be expected. However, I will note that our emission rates that we found were they were higher than the emission rates estimated by Allen et al. Another interesting result was that the largest ethane emissions were seen at these sites, and this actually makes a lot of sense because they were located in the wet gas region of the Marcellus, which is in Washington County. You'll notice here at this well site, it had very high ethane emissions and very high variability in those emissions. So if you look at the molar ratio of ethane to methane, you can see that there are two distinct slopes, indicating that we saw two distinct emission sources at this site. The lower slope is thought to be from just routine fugitive losses, and then this upper slope is likely from tank flashing emissions. And what's important here is that we saw these flashing emissions in a 2-hour sampling period. So it's interesting, what role do these site processes have on the overall emissions? So longer monitoring is really crucial to understand what the overall role these processes have. So then looking at the drill rig we investigated, the emission rates here were much lower than estimates by Roy et al. For drill rigs. In fact, NOx was a factor of 10 less. A surprising result was that we saw methane enhancements downwind of this drill rig. And this is thought to come from a natural gas kick. And this was actually similar to the results seen at or observations by Carlton et al. Using aircraft measurements. Then finally, the flare completion site that we looked at. At this site, we observed two distinct plumes downwind of it. One was from the hot buoyant flare, and this we found, we intercepted about 1.5 kilometers downwind. The other plume is thought to come from ground-based emissions either fugitive losses or processes that are occurring before the flare. And so if we look at the temporary flare plume, what you can see is we observed enhancements of CO and CO2 in that plume, but we did not see enhancements of NOx. And at the same time, we saw decreases in organic compounds in this plume. And so that's telling us that this flare was very efficient and in fact had a modified combustion efficiency greater than 0.99. Ground-based emissions at this site, there had very large variability over the 3-hour sampling period and very high emission rates of the species we monitored. In fact, NOx had a mean center plume concentration, max center plume concentration of about 140 ppb. Methane emissions were the highest we observed in this study. You can see here that our average emission rate was about 8 tons per day. And this is in excess of the emission rates estimated by Allen et al. For completions, which has a upper bound of 3.3 tons per completion. So this is very significant because completions can last up to several weeks. So based on these results, it looks like ground-based emissions at these completions likely have a larger air quality impact than the flares themselves. The final thing I want to talk to you about is background concentrations in the Marcellus. We were monitoring while we were driving between the sites. And so because we were in a mobile lab, there were interferences from on-road emission sources. And so to isolate the background while we were driving around, we developed this, this percentile interval analysis to isolate this background, and this is an example of what it looks like. And we can use that to then compare the background concentrations throughout the Marcellus region. You can see differences between the northeast and southwest. We can compare to other studies in the Marcellus, for example, the Carlton background via aircraft measurements or measurements from other shale plays. This type of results can also be used for further analysis, which we're working on now. So here's a summary slide here. I guess I'll just leave that for you to read and then take any questions from you.
We have time for about 2 questions.
I think.
Where? Oh,
yeah.
There you go.
For the sites that you're looking at that were in active production, do you have any sense of how comparable they were to one another in terms of like kind of well and active production rates?
Yeah, they had fairly similar production rates, actually. Interestingly, the one that had the lowest production rate had the highest emissions of methane, though. So, yeah, in the back.
What's the natural gas kick?
Okay. Yeah, that's when the drill actually encounters a pocket of gas in the ground, and then it is directed up through the drilling mud. And I believe it's sometimes treated at the drill rig. I don't know a whole lot about it. I just know that it exists.